Yes.
Yeah, he planted the seed.
Yes.
Red herring.
Not the answer.
These are the droids. Yes.
Yes.
So for double or nothing, what is the formula you were supposed to remember from last time?
We're supposed to remember all of that.
Yes. So mx t iid rb, we have mu and sigma, zn was equal to x1 plus xm minus mu over sigma square roots of n. Right? This was mean 0, variance 1. It's recording?
Yes.
Okay, it's recording. And unfortunately, I can't just look at the video for what we had last time. But this is the formula you're supposed to remember, so we don't have to go back to the beginning. It was, I think, e to the negative mu square root of n t over sigma mx t over sigma root n to the nth power. Right? So we proved this last time. And we were very careful to argue in great generality. So when we're doing sums of Poisson, the reason I wanted to do that is Poisson is double exponential. When you take a logarithm, it's no problem. So if we take the log of m zn of t, okay, we're getting negative mu square root of n t over sigma plus n times the log of mx t over sigma square root of n. And the goal is show it converges to what? Excellent. T squared over 2. How can I write t squared over 2? How t squared? Well, how else can I look at the 2?
2 factorial.
2 factorial. So do you think it's a 2 factorial or do you think it's a 2?
2 factorial.
Did we think it might be part of it? Did we say that
Yeah.
it was 3 factorial for the
That's for the correction terms.
correction terms?
Right.
So assume that it's...
So one possibility is maybe this really is a 2 factorial just in terms of how I should be thinking about it. It's coming from a Taylor series expansion. Now, this is also coming from taking the log of the moment generating function of the standard normal, which was e to the t squared over 2. So in the standard normal, I have this 2 coming in. But here, I really want to be thinking of this as a 2 factorial, as I'm going to be having a Taylor series coming in. So I want to try to understand the log of the moment generating function evaluated t over sigma root n. Well, I have a series expansion for this. I'm assuming my moment generating function converges in a neighborhood of the origin. As I go higher and higher and higher, as I go further and further down in the Taylor series expansion, the terms are going to matter less and less. Why? Well, the series converges, and I'm evaluating it at t over sigma root n. This is a really small number. And so eventually, the square root of n is going to be growing so fast and t is fixed that the higher terms won't matter. Now, I am multiplying it by n. n is large. So what that means is the first few terms of these could actually matter when I expand things. They better because I have a square root of n over here that I have to balance. Okay? If I give you any probability distribution, what is the 0th moment? 1. So when I look at this, this is the log of 1 plus something small. I have a chance of understanding this, right? The log of 1 plus something small, that's going to be something small, okay? If it was not 1 plus something small, if it was like 2 plus something small, I would be in trouble. I might not be able to cancel everything. Because I've got this big n outside, and n times the log of 2 would be much larger than this, it would just explode. But because the moment generating function starts off as 1 plus something small, it's extremely likely that everything will work at the end of the day. Also, I wouldn't be giving this lecture if it didn't work out at the end of the day. All we have to do now is go through the algebra. Do you think we want the Taylor series expansion for the log of 1 plus u or the log of 1 minus u? What do you think we want? So what does the moment generating function look like? It looks like 1. So mx I'll just use the letter U right now, is 1. What comes next? This isn't good.
The mean.
The mean. So 1 plus mu U plus mu2 prime u squared over 2 factorial plus mu3 prime u cubed over 3 factorial. So I can bracket that whole quantity. It's 1 plus something. So I'm going to want the Taylor series expansion of the log of 1 plus something. And in fact, I can write this as 1 plus u plus mu2 prime over 2 u plus mu3 prime over 3 factorial u squared plus dot dot dot. Okay. So now, if I look at the log of 1 plus x, this is x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. So this is what I get when I look at the log of 1 plus x. So everything I'm doing now should be in the book. It's just algebra from this point. Okay? It's just going through the algebra. The difficulty is we no longer have a closed form expression for the moment generating function. So I have to go through just this general Taylor series expansion. Fortunately, we don't need to go deeper than second order. Okay? If we needed to go deeper, it's not so bad. It's just more algebra. Okay? There's no new idea that's needed. It's just patience. So now, the log of mx of t over sigma square root of n. So this is now the log of 1 plus u is t over sigma square root of n. And now inside I get mu plus mu2 prime over 2 factorial u, which is going to be t over sigma square root of n, plus the next piece, I'm going to just write it like this. T squared over sigma squared n. And this just means an error that's on the order of t squared over sigma squared n. Yes?
We can add in that 1 because the thing is so small.
I'm sorry?
We can add in the 1
What
against the
do you mean
log.
by...
Like that when we do log 1 plus x, where did that 1 come from?
Over here?
Yes.
No, I'm just saying this is the Taylor expansion of the function log of 1 plus x.
Okay, but then when we're sort of looking at the log of the moment generating function.
Well, the moment generating function,
Oh.
this is just, it starts off with a 1.
Okay.
That's why I want to do the Taylor series expansion of the log of 1 plus x and not the log of x.
Okay.
The Taylor series expansion of the log of x is not so good. But if x is very small, then the log of 1 plus x is very close to the log of 1. What's the log of 1? 0. So the idea is whenever you have a Taylor series expansion, it's useful if you're expanding about a point you know. If I had to give you a point to do logarithms, you'd probably want the point 1. Right? And so we expand around the point 1. And so this here just means, error on the order of t squared over sigma squared n. And the reason is if you look at what happens for all the other terms, you can do a little bit more bookkeeping to be a little bit more rigorous. I don't really want to go through all that algebra. We have a series that converges. And for all the terms from this point onward, every term has at least a u squared. The next term has a u cubed, a u to the 4th, a u to the 5th. I can pull out a u squared, and then I have something that converges. And I can then bound that independent of t and n. And the reason I can do that is I know this number is going to be at most delta, and I know my series converges for any input into most delta. I can put in some kind of bound. Okay? I just want to save you some of the algebra. Not all. I want you to experience some of it. But, trying to minimize a little bit of how much we're going to go through in the board. If all 5 blackboards were accessible, maybe. But is everybody comfortable with this? All the other pieces have at least a u squared. I have a series that converges. T over sigma root n is eventually going to be less than delta. So it's going to converge to some number. So the error here, maybe it's 2 billion t squared over sigma squared n. Is 2 billion big? It's always relative. Is 2 billion big relative to what? Williams' endowment. Is 2 billion big relative to Williams' endowment? No, it's actually comparable. Right? Is 2 billion big relative to the national debt? No, it's small. You know, is 2 billion big relative to the amount of money you have in your wallet? If the answer is no, see me after class, we'll talk. Okay? You know, we could use a really nice new building for the sciences. Okay? What is 2 billion? You can't answer that question on an absolute scale. It's got to be relative to what? Relative to n, well, n is going to infinity. 2 billion is a fixed number. As n gets very, very large, it doesn't matter if I multiply this by 2 billion. It's still going to go to 0 rapidly. Now I start expanding everything out. And so when I expand this out, the first thing I get is I get the x term. So that's this whole piece. So I get t over sigma square root of n u plus u2 prime over 2 factorial t over sigma root n plus some error of size t squared over sigma n. Now I subtract off x squared over 2. So now I subtract off 1/2, okay, x squared, so I have to square this whole thing, so I'll get t squared over sigma squared n, and now I square the whole thing inside. U plus u2 prime t over 2 sigma square root of n plus e t squared over sigma, oh this is sigma squared here, sigma squared n plus dot 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 dot. Do I have to worry about the dot 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 pieces? They're all going to involve an x cubed and x to the 4th. I have a t over square root of n. The next one starts off with a t squared over n. What's the next one going to be? So the next one will be t cubed. I don't care about t, I actually care about the n dependence. What will be the n dependence on the next one? T cubed over n to the 3 halves. The next one will be t to the 4th over n squared. Then t to the 5th over n to the 5 halves. So the next piece is going to involve a n to the 3 halves down below. We multiply this by n. We have n times the logarithm. So if I put back the n, so if I have n times the log, I have an n over here, I have an n over here, and now all the other pieces over here, they'll have an n, and the best I can do is n divided by n to the 3 halves. That's a 1 over square root of n, it's going to tend to 0. So all these other pieces I can actually replace with an error of size 1 over square root of n. And this error, it can depend on t, n, and delta. But it's just some error of size 1 over square root of n. Okay? As n gets very, very large, does it matter? No, it's going to go to 0. If I wanted to estimate how quickly does this go to 0, do I need to keep track of that term? Yes. If I just want to show in the limit it's converging to a Gaussian, do I need to keep track of that term? No. And so we're not trying to estimate rates of convergence. If we were, we would have to do more work, we would have to keep more terms, but it's no new fundamental idea. It's just a more careful bookkeeping. It's just more algebra. And the nice thing is it's a one-time algebra cost. And you'll see then the third and higher moments coming into play. Alright, let's look over here. So I have nt mu over sigma square root of n. So I get mu t, well, I'll write like this, mu square root of n t over sigma. Next is I have this hits this piece over here, plus n square root of n square root of n. Those cancel. I get u2 prime t squared over 2 sigma squared. The only thing that cancels is the 2 root n's cancel with the n. and the two sigmas reinforce, the two t's reinforce. The next one is I have a square root of n from this, and this is a t squared over n. What does that piece look like? So I have n up top, a square root of n, and an n down below again. What does that piece look like?
The error function's one there.
Yeah, it looks like another error of 1 over square root of n, plus some error of size 1 over square root of n. It's not going to matter in the limit. So really, the only terms that matter from here are the first two. This third term is going to be too small. This is our t cubed term. It's t cubed over n root n. And when I multiply by n, it's still small. Now let's look at the next one. Now over here we have n t squared over 2 sigma squared n. Oh, okay, this is great. This is t squared over 2 sigma squared. There's no independence. So any of these terms that have n over here, are they going to matter in the limit? No, they're going to go to 0. The reason this term mattered is I was multiplying it by something huge. I'm no longer multiplying these by anything huge. So when I square this, what's the only thing that matters when I square this?
The mu squared, right?
The mu squared term. Your mu times mu, that will contribute. Mu times this won't contribute. It's 1 over square root of n. Mu times this won't contribute. This times itself won't contribute. It's a 1 over n. This times this, even worse. So the only thing that really matters is the mu. So I get n, the n's cancel, and I get mu t squared over 2 sigma squared plus an error of size 1 over square root of n. And then I still have my error of size 1 over square root of n. So let's look at the national debt again. Let's say you owe $1 million, $2 million, and $500,000. Is the sum of those three things large or small relative to the national debt?
Small.
Small. I have 3 small errors. If I add 3 small errors, it's still a small error. What if I added n small errors? Could that be large? Yeah. If I add n things that are of size 1 over square root of n, how large could it be? It could be square root of n. It could be huge. Right? So it's very important that I only have a fixed number of errors. I only have 3 errors. 3 errors, no problem. So now I just collect. Doesn't matter, doesn't matter, doesn't matter. Alright, so I have mu square root of n t over sigma, which will perfectly cancel what we have over here when we take our logarithm. Now the t squared term, both of them have a 2 sigma squared down below. And then we get mu2 prime. Oh, we have a typo. What's the typo in this line? It's supposed to be mu squared. We have mu2 prime minus mu squared t squared. What is mu2 prime minus mu squared? The variance, right? mu2 prime is the second moment. Mu squared is the square of the mean. This is the expected value of x squared minus the square of the expected value of x. So we have sigma squared divided by sigma squared. What does that equal? 1. So this is just equal to mu square root of n t over sigma plus t squared over 2. And this was the log of the moment generating function at t over square root of n times n. We now have to plug that into our formula for the log of mzn of t. And when we put it in for the log of mzn of t, the negative mu square root of n t over sigma will cancel the mu square root of n t over sigma. And so we get the log of mzn of t is, oh, and of course I still have my error over here, right? Plus an error of size 1 over square root of n, plus an error of size 1 over square root of n, will just be t squared over 2 plus an error of size 1 over square root of n. And this goes to t squared over 2 as n goes to infinity. And that finishes the proof. Okay? And you can see that if you cared more about rates of convergence, you could easily keep more terms. The difficulty is then how to convert from knowing what your error is in the moment generating function to what is your error in the cumulative distribution function. There should be a way to pass from one to the other. If I know my moment generating functions are this close, what can I say about the cumulative distribution functions? Well, if the moment generating functions are close, the moments are close. If the moments are close, the probabilities should be close. This is not always true. You know, we had those two functions that have the same moment generating function, but different densities. So there are some technical issues. But it seems reasonable that we should be able to deduce something. Okay? This is the proof of the central limit theorem modulo, two results from complex analysis. And what I like about this proof is you can see why it's just the mean and the variance that matters. The higher moments of the probability distribution only come in low order terms as the error. They affect the rate of convergence. This is why you have such universality. The central limit theorem should be shocking the first time you hear it. It doesn't matter what I'm adding, as long as they're nice and independent, that's going to converge to a normal. Exponential, Poisson, coin flip. There's basically only one thing you have to stay away from, the Mobius coin. The one-sided coin that's always heads. That's not going to converge to a normally distributed, right? It'll just converge to how many times you toss it, that's how many heads you get. You stay away from that. And as long as your distribution is nice and has, say, up to finite third moment, you will converge to a normal distribution. Okay, any questions on the algebra of the proof? So what I want to do is I want to talk just a little bit more about other ways to attack the central limit theorem, and then talk about a defect of the moment generating function. All right. I know some people have had job interviews and have been traveling. Has everybody here done the first 3 problems of the exam? Okay. So, question. Find a random variable such that the moment generating function does not converge in a neighborhood of 0. So can somebody give me a random variable whose moment generating function does not converge in a neighborhood of the origin? Yes.
Country distribution.
You're guessing or you're positive?
I'm guessing.
Why are you guessing that?
Because it doesn't have the second moment.
Yeah, it doesn't have second moments, may not even have a first moment. So as a really good guess, Cauchy distribution is an outstanding choice. So let's look at x is Cauchy. So then the moment generating function of x would be the integral from minus infinity to infinity of e to the tx 1 over pi 1 over 1 plus x squared dx. And this is just the expected value of e to the tx. So if this converges in a neighborhood of the origin, then for all t less than delta in absolute value, this should make sense. For which values of t does this converge? So you should be able to give me at least one value of t where it converges. What's one value?
0.
0. Can you give me any other values where it converges?
Any negative.
Any negative value. Because if, really?
Oh.
So if t is negative,
Yeah. When you get
then when x is negative, we have problems. Right? So for negative values of t, the integral from minus infinity to 0 blows up. Okay? What about positive values of t?
X is negative.
So if t
Or
is now
if x is
positive,
positive.
if x is positive, it blows up. So converges for t equals 0. You know, big deal, right? When t equals 0, I'm taking the expected value of 1. It's not that impressive to calculate the expected value of 1. That's the only value of t that works. So this function's moment generating function only converges at the origin, where we have essentially forced the moment generating function to converge. We cannot deal with sums of Cauchy random variables. And there are workarounds to deal with this. If you've heard of the median is a nice workaround for this. And you can actually talk about the median of a Cauchy random variable. And it turns out that the median of a sum will frequently become normally distributed about the median. And so if people are interested, that's something we can talk about, you know, towards the end of the semester. So what we look at instead is what's called the characteristic function. It's also called the Fourier transform. How many of you have heard of the Fourier transform? So analysts will call it the Fourier transform, probabilists, and I think that is the word, will call it the characteristic function. So I'm not sure what notation I should be using for this. I'll use C. Cx of t is going to be the expected value of e to the I tx. And if you look at this, you really should be going, really? That's all you're doing is you're just putting in an I in the exponent? Yes. And so that's now the integral from minus infinity to infinity of e to the I tx in the density of x dx. The advantage of the characteristic function is that it always exists. And it exists for all values of t. And the reason is e to the I theta is cosine theta plus I sine theta. The absolute value of e to the I theta is always 1. How many of you have seen this relationship for e to the I theta? How many of you have not seen this? Alright, so if there's some... I'll just briefly do this. How many of you have seen trigonometry, all of trig in like 5 minutes? All trig follows from this formula. So let's do this. Alright, e to the x is the sum of x to the n over n factorial. N goes from 0 to infinity. Okay, everybody agrees with that. Cosine of x is the sum of x to the 2n negative 1 to the n, x to the 2n over 2n factorial, and goes from 0 to infinity. And this will give you your 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, dot, 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 dot. Sine of x is the sum, n goes from 0 to infinity, of negative 1 to the n plus 1, x to the 2n plus 1 over 2n plus 1 factorial. No, I want to do... And this will give you x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus dot, 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 dot. If you just formally plug in e to the ix as the sum, n goes from 0 to infinity, of ix to the n over n factorial, where I is or I am the square root of negative 1, so I squared is negative 1, I cubed is minus I to the 4th is 1. Basically, when n equals 0, I'm going to start off with 1. When n equals 1, I'm going to get ix over 1 factorial. That's this term multiplied by I. When n equals 2, I'm going to get an I squared, which is a minus 1. Oh, that's this term. When the dust settles, you get cosine x plus I sine x. And so this is a wonderful formula. What's e to the ix times e to the minus ix? 1. This 0, which is 1. We proved in this class that when you have exponents, e to the x, e to the y is e to the x plus y. Right? So now if I look at this, this is cosine x plus I sine x times cosine x plus I sine of negative x. Well, the sine of negative x is what? It's negative sine x. So I can pull this outside. And when you do the algebra, cosine times cosine is cosine squared x, plus I sine x cosine x, minus I sine x cosine, oh, that cancels. And you have I times minus I is 1, plus sine squared x. This is Pythagoras. Let's do one more. E to the I x, e to the I y is e to the I x plus y. This is cosine x plus I sine x, cosine y plus I sine y. Well, e to the I x plus y, by definition, that's cosine x plus y plus I sine of x plus y. We're going to get our trig formulas. We're going to get the angle addition. On this side, what's the real part? Cosine x, cosine y. And now, this is going to be imaginary. This one's going to be imaginary. Then I times I is minus 1. So I get minus sine x sine y. And now I have the imaginary piece. So the imaginary piece is going to be I times sine x cosine y plus cosine x sine y. Well, if I have two complex numbers, the only way they can be equal is if the real part equals the real part, the imaginary part equals the imaginary part. This is the cosine of x plus y. This is the sine of x plus y. You can get all your trig like this. You want the double angle formula, you want sine 2x, take y equals x. You want half angle formulas, I feel like a used car salesman. Whatever feature you want from trig, I can get you from this. Okay? All you need to remember is e to the ix is cosine x plus I sine x, and that exponents add. E to the ix, e to the iy is e to the ix plus y. All of trig follows from this. Okay? If you don't remember this, I think the way you typically prove the angle addition formulas is the following. Here's x, here's the angle y, here's the angle x plus y. You drop the perpendicular to here, you drop the perpendicular to here. That's not really enough. I drop the straight line like that with a perpendicular over here. And I can figure out, right, and I drop this line here. So I can figure out what this length is here. I can figure out what this is. I can figure out what this is. And you can play all these different, geometry games to get the sine of x plus y. So if this is 1, this whole length here is going to be the cosine of y. This will be the sine of y. I now have a right triangle. I can figure out how things pass through. Okay. You can play these triangle games, and I urge you to do that if you, want. If it's been a while, you probably should try to see if you can make that work out. This is much faster, but needs to use calculus. So, why am I going through this digression? It's to talk about the characteristic function. The characteristic function is fundamentally a complex object. It needs e to the I theta. Too many students make it to their senior year without having seen e to the I theta or complex numbers. And so I will make sure that you will not be one of those seniors. Okay? This function always exists. So a big part of upper level analysis is called transformation theory. Is given one function, you transform it into another where it's easier to extract the properties you want. The difficulty of the moment generating function is it doesn't always exist, so it's really not a good idea to transform your function to something that's not there. The characteristic function does exist. If I can figure out the characteristic function, can I figure out the moments? Yeah, the moments I can just Taylor expand e to the itx in some sense and try to play games like that and try to get the moments as well. If I differentiate this with respect to t, and ix comes down, oh, I get the mean. Okay, I get the mean multiplied by I. I can live with the mean multiplied by I. If I want the second moment, I take two derivatives, and I get the second moment multiplied by I squared or negative 1. Again, not a big deal, I can live with that. So you can recover all the moments from the characteristic function. It has the disadvantage of being complex valued, but it has the advantage of always existing. And typically that's a good trade. Alright, so this is going to be all we will do for the characteristic function, but in general probability theory, this is typically what's used and not the moment generating function because of these technical reasons. Okay. Any questions on what we've done so far? Alright, so we've got about, 10 minutes left? So I thought it would be nice to do another problem that's extremely algebra intensive because we haven't done nearly enough algebra and symbolic manipulation today. Except, unlike what we've done earlier today, this is something where we can actually solve it in one line. So this is the bug problem. And so, fix a p in 0, 1. So if p equals 0, p equals 1, the problem is not that interesting. So, bug dies with probability p, splits into 2 bugs with probability 1 minus p. So maybe instead of a bug, we should probably be thinking of maybe a bacteria or something like that. I kind of like the idea of this kind of strange mutant bug. Okay? What do you think happens next? It repeats. So, if split, each bug independently does the above step. And you just continue. At each stage, each bug independently splits as above. So no 2 bugs can ever impact each other. So what is a natural question to ask? There's several questions you can ask. I gave you one to think about for today, but there's other questions you could choose to ask. And please, nothing about the mechanics of how the bug does this or what's going on. Mathematical questions.
How many splits will there be?
How many splits will there be? Great question. Relate to that, how many bugs do I have at a given time? And then the one I gave you is, do the bugs eventually die out? Do the bugs die out? Let p sub d be the probability they die out. Can somebody give me a long, painful way to calculate the probability they die out? Yes. So you promise it's going to be long and painful? Right? Okay.
Calculate the probability they die out in the first stage, and look at all the options for the second stage, meaning either it died or it didn't die, and calculate the probability it died out for us, and just keep repeating.
Good, that would be very long and painful. Right? So, what's the probability that they die out in the first stage?
P.
P. What's the probability they die out in the second stage?
1 minus p.
Okay, good, so we have to get to the second stage. So we have a 1 minus p
times p squared.
times p squared. Right? Because in the first stage it splits into 2, and then both bugs have to die. So here, death. Here, split,
So it's a sum for.
and then death.
It's the sum as n goes from 0.
Let's do one more. Let's do one more. What's the probability that they die in the third stage?
1 minus p squared.
To the third.
1 minus b squared times
Goes to the third.
Oh.
It depends how many dots.
Yeah,
into the
there's like a
second.
couple things.
There's a
One
couple
thing
of different
squared
possibilities.
early and
Let's
one
look at all the different things that can happen. So first, we know this has to happen in step 1, right? The bug has to split. And then at least one of these two has to split, but not necessarily both. So we could have this happen. We could have this happen. And we could have this happen. And then we'll put the little deaths. They're only routine bugs, don't worry. Okay. So now the probability that we die out in the third stage is we have to make it there and then we die. So what's the probability of this? So it's 1 minus p to get here. And then this is a p, and this is another 1 minus p. And then we have a p squared. So I think it's 1 minus p squared and then p cubed. And then over here, same thing. And this one,
One minus p cubed p to the fourth.
yes. How much time do we have left? Oh, okay. Right, we have plenty of time to keep doing this, right? Plus, dot, dot, dot. Okay? So this becomes a great introduction to graph theory. These are technically known as trees. How many different trees can I have of order 4? Where they go down 4 levels deep. And then you've got to figure out all of those. And then you've got to figure out what the hell the sum is. Okay? This should look like a very painful problem. Okay? The problem can be solved in one line. Okay? So before we do it in one line, is everybody convinced that this is a painful problem, that this is algebra you do not want to do? Okay. If you don't, it's even more important than if you have $1 billion in your wallet that you see me if you think that this is something pleasurable. Right? We definitely need to talk. Okay? We do not want to do this. Let's think about what's going on. Does this remind you about anything you've seen in the semester?
Basketball problem.
The basketball problem. Excellent. All right, make sure you email me. Oh, this is the basketball problem. Right? Why does it remind you of the basketball problem?
Because it's the it's like the chance the first person makes it and so you like can hopefully define the recursive.
Okay, so hopefully we do. So PD is you die on the first step. Or if you don't die, you split into 2. And now, there's some possible happening from each of these bugs. What's the probability that this line dies out? PD. What's the probability that this line dies out? PD. So I didn't want to use the letter X to hide the fact that this is the basketball problem. Right? So we now have, if you let X equal PD, you get X, oops, sorry, this should be an equal sign here. X equals P plus 1 minus P times X squared. So you get 1 minus P X squared minus X plus P equals 0. So you get X equals 1 plus or minus the square root of B squared minus 4AC. So it's going to be 4P 1 minus P divided by 2A. And that's the solution. So So now what you want to do is you want to play around with different values of p and see what happens. We have 5 minutes left. Great. So let's just look at this and try to analyze. Can anybody, yes?
Is this considered a memoryless?
This is a memoryless process.
And that's different from recurrence tradition, right?
So a lot of it's going to depend on how you want to define things. So we're not returning necessarily to the same state as before. So in terms of being memoryless, it's technically not exactly memoryless, but we've returned to the initial state.
Like for each branch.
Right, so each branch has returned to the initial state. The whole process hasn't restarted. So it's not maybe technically the same as memoryless, but it's a situation where that same general idea is happening. Is we've reduced it to now 2 copies of our initial state. Yes.
P and P equals PD, I'm assuming. Then, or why don't you have to keep on going?
What do you mean? Oh, in here?
Yeah.
Well, I'm saying if PD is
Oh,
the probability
okay.
that one bug has its line eventually dying out, then at this point, I just want to know what's the probability that this line dies out, what's the probability that this line dies out, what's the probability both lines die out. It's just going to be PD squared. And so this will give us the probability, this will give us that monster formula. So what values of P can we understand first? What's a good value of P to try?
1/2.
1.
Well, I mean, 1.
Technically I'm not allowing you to do 1.
So
Well,
you
let's
said no 1 and 0, so I said 1/2. No.
So now you're going to start listening to me? I mean, all the times you guys give me smart aleck answers. Okay, so I'm technically not allowing you to look at 1 and 0, but still, look at 1 and 0. Now, I claim it's not going to be interesting as to what happens. So let's see, if P equals 1, the probability that the bugs eventually die out is 1. Now, things blow up.
Yeah, you know, a little.
So did we make an algebra mistake somewhere?
This is sort of pointing out that it's a foolish question. I think that you remembered you said something about like in physics, like how if you have the denominator, it's like 1 minus 1. Like if you get a 0 in the denominator, that's like a way of sort of showing you, oh, like this is something that's self-evident. I remember you talking about something similar to this.
Well, I'm saying if we put in P equals 1, this blows up. And there's no way I can use L'Hopital to cover myself here, because I've got, oh, wait a minute, I've got 1 plus or minus the square root of 1. Oh, wait, maybe I'm okay. Right? So one of the roots will be plus infinity, which is not really reasonable. But the other root is going to be 0 over 0. It's an indeterminate. So there is a chance, right? So if I take P equals 1, this vanishes. I get 1 minus 1, which is 0, over 2 times 1 minus 1.
Why do we
just
just
plug it into that?
Because if we don't even have, we have a quadratic equation with like
Yes.
x squared from
So
0.
we'll do that in a moment. I just want to show that this formula actually survives. Okay? So when you do put in P equals 1, you get 0 over 0. You can then Taylor expand the numerator and try to extract information from that. But as has been suggested, and you can get M&M's afterwards, I don't know how many people are saying this, just go back to this quadratic equation. We have a 0 coefficient in front of x squared. Do not use the quadratic equation for linear equations. Okay? The ante to use the quadratic equation is having a quadratic equation. We can't use the quadratic formula here. Alright, so we're left with negative x plus p equals 0. Okay, x equals p. Alright, so we've got a phantom root. Alright, so if p equals 1, everything is fine. What if p equals 0? What should we get? And so when we put in p equals 0, we get 2 for the denominator. We get 1 plus or minus 1. So the roots we get are 2 over 2 and 0 over 2. So when p equals 0, we have two possibilities. Either it always dies out or it never dies out. Which do you think is correct? Never dies out. But you know, this is one of the difficulties is quadratic formulas can introduce extraneous roots. And so when I do this kind of not quite remember this, but when I do this kind of repetition, I can actually introduce an extra root. And you need to use a little bit of common sense. If the probability of a bug dying is 0, then the probability that the bugs die out should not be 1. Okay, because no bugs ever harmed each other. Then the question becomes, what can you say about other values of p? And so I will leave you to plot that and put in different values of p, because time is now up. Okay.